demonstrated. So the recording has started. I will add a new location to the project to represent my system. And I can just give that a name. I'll just give it a very generic name for this example. I can give it a description. I can add additional notes as well. Just a side note, all of these headings are customizable, so you can make these say pretty much whatever you want. You can do that through the project options. But I'll click OK, and that adds a location. And I can highlight that location and add something else beneath it, another location perhaps that might represent a subsystem or an equipment or something like that. I'll just say this represents maybe a piece of equipment upon which I am performing maintenance. Click OK, and that gets added to my hierarchy as well. I can have as many locations as I want in the hierarchy, and I can go down to as many levels as I like, so there's no limit to the number of levels I can place in the hierarchy. I can have as many as I want. So in RCM, we start by defining the functions of the equipment or the assets that we intend to maintain. So in RCM cost, we can do that as well. I can go to add resource function, or I can add a function from the toolbar. The function object is relatively simple. It's just a description of what that equipment does. So I would just enter a text description and click OK. And there is the function of that equipment. Each equipment, each location at the root of the hierarchy can have as many functions as it needs. You can have as many functions as you want. So I could have a whole list of functions that are performed by this equipment if necessary. I'll just leave it at 1 for my example. Next, in RCM, we would define what are the functional failures of the equipment. How does the equipment fail to perform the functions that we're asking of it? So again, I can select the function, and now I can click Add a Functional Failure. I click, and I can enter a description of the functional failure. And each function can have as many functional failures as it needs. You can have as many as you want per function, as many functions as you want per equipment. There are no upper limits on any of those things. So the next stage in RCM would be to ask, well, if these are the functional failures of our equipment, then what are the causes of those functional failures? You can add a cause in RCM cost, and in fact, the cause in RCM cost is actually where the majority of the information will go into your analysis. The cause is perhaps the most complex object in RCM cost. So I select the functional failure and I add a cause. So I'm just going to give that a description as well. And you can see actually there are lots of text fields where you can describe different aspects of the failure cause that you are analyzing. Now, as I mentioned, the cause is where much of the information goes into your RCM cost analysis. You can have as many causes as you want per functional failure and throughout the project. And each cause will represent a possible reason why your system might undergo a functional failure. So when we simulate failure, repair, and maintenance, we need to give the program quantitative data to work with. We need to tell the program about what are the expected failure trends for each of these failures that we're looking at. So we might start by taking a look at the failure tab. So on the failure tab, we can enter information about how often the equipment might be expected to fail because of this problem, whether or not this problem is associated with wear out or fatigue and other aspects, other types of failure trend. Now, there are several approaches you can take to this. The first, perhaps the simplest, is to just enter the failure data manually. So here, for example, I've chosen an exponential distribution which represents random failure. And I've entered a mean time to failure, and it's very, very simple. So for example, if you've got a new piece of equipment and the manufacturer has given you an estimated mean life or something like that, you might enter that in this way. Now, sometimes if you're working with a brand new system, maybe a greenfield site, and you don't have any information to work with yet, you may need to make estimates based on your own knowledge, your own experience, and that of your colleagues and any consultants that you're working with. So a framework for that is provided in the form of the failure distribution wizard. That can be accessed via this button here. And here I can tell the program what types of failure behavior I expect to see and what are the characteristics of those failures. So for example, I could have a failure that follows a bathtub curve. So I can say, well, I expect to see random failure and wear out and infant mortality. So I can cover any and all parts of the bathtub curve. I can then enter what I expect the random failure rate to be. I can enter when I expect failure, when I expect wear out to begin and how long it takes for most of the equipments to fail. And I can say when I expect infant mortality to occur and what's the average failure rate for that. So this information would come from our discussions with our colleagues, with consultants, and we can base these estimates on our own experiences and our own knowledge. Now, the other end of the scale, you might have a system that's very mature and you have a lot of historical failure data, perhaps built up in a CMMS or in an ERP system like SAP or Maximo. And from that historical failure data, you can build a viable analysis in the viable module, which I mentioned earlier. You can do a statistical analysis of the history of the equipment, and from that, estimate the failure behavior. Does it follow a wear out curve, or is it random failure? What is the life expected to be? I can then reference that viable analysis in the viable set drop-down box, and the program will simply pull in the results of that viable analysis and use that as the basis for simulating this failure. Now, I'm going to select something fairly simple. I'll choose a viable distribution, and I'll say maybe it's expected to last for 5 years. I will enter that in hours, and it's got linear wear out. So I've got maybe some fatigue in the system, and the average failure time for fatigue is about 5 years. Now, obviously, there's a lot more going on here as well. I won't go into detail on that today for a relatively short webinar, but there's lots of other things that you can model, as you can see, and maybe we'll come back and look at some of these things a little later. But for now, we've defined some failure characteristics for this particular problem. And we can take a look at the maintenance. On the maintenance tab, we can define the different tasks that take place in order to tackle this problem. So naturally, if there is a failure, we might expect there to be a corrective task, a repair that we can perform to fix this problem. So that's defined automatically by default. You can see it there. I can edit that. I can enter a description of that task, and I can enter information, say, about how long I expect the task to take, what's the operational cost of that task, and maybe also the resources that are required as well. So the resources will cover things like labor, equipment, or the tools that we use for the maintenance, and spare parts. And if I want to, I can include all of those in my task. It's not mandatory to include this information. If you don't have it available yet, you could just make an estimate of the overall cost of the task and enter it as an operational cost. However, you can also break down your costs by the different resources, and then you would get more detailed results when you analyze the project later. So I can add maybe a labor category. Now I can select a labor category from a pre-existing list that I've created earlier, Or if I don't have any yet, or I can't see that the labor category I want, I can just create a new one. So maybe I'll call this one engineer, and I can say how much it costs to call this person out for corrective tasks and for scheduled tasks. I can say how much it costs per hour while the person is working, and I can say how long it takes for them to get to the site of a repair. So I might enter some of this information just based on what I know about having this person working on site. And then I can sort of say how many of these people I need and then add them to my resources. I can do the same for equipment as well. I won't show you that because the information is actually exactly the same. But that just allows you to enter information about the tools you use. Maybe it's a crane or a truck or something else. We can also add spare parts. Again, I can create a list of spares that I can reference here, or I can just create a new one. I'll call that just spare. I can say how much a new spare part costs. I can say how many I can store and where. Levels 1 and 2 represent on-site and off-site spare part storage. So level 1 is where I keep my spares nearby. So I might say I have one of these on site and it costs this much to store them and it takes this long to get one from storage. And maybe at level 2, I can keep 5 of them and it's a bit cheaper to store them there. And the logistic delay is just a bit longer. So maybe it takes 6 hours to get the spare from level 2. If I don't want to use level 2, I don't have to. I can leave all these values at 0 and the program will just ignore level 2. But I can model all of these levels if I want. Level 3 is supplier. So I can say how long it takes to get a new spare part from the supplier. Maybe in this case it takes 1 month. So I can model the spare pretty much in as much or as little detail as I need to. So I'm putting in quite a lot of detail in this case. I'll click OK. I'll say I need 1 spare, and that gets added to my list of resources as well. So I can start to build up quite a detailed picture of the maintenance, of the repair of this particular problem. So I'll click OK, and that updates my corrective maintenance. Now I can also create scheduled maintenance, and there are 2 different types of scheduled maintenance we can create. The first of those is planned maintenance. This is maintenance that takes place at regular intervals in order to improve the condition of the system. So that might be something like a scheduled replacement, or it might be lubrication, or some kind of cleaning or decontamination. So I can add a planned maintenance task. I can say how frequently that task takes place. So, how often am I doing this maintenance? And then the rest of the information is very much similar to what we saw for the corrective maintenance. So I might say this task takes 2 hours to perform at an operational cost of maybe 500. I can say who I need to do that maintenance and any other resources that are required as well. Now you may have noticed on the corrective maintenance dialog, there was also an advanced tab. You'll see that here as well. The advanced tab lets me set up a few things like what condition is the asset in after the repair has taken place? Is it as good as new, meaning maybe I've replaced it? Or is it as good as old, meaning I've just done what's required to get it running again, but nothing more? Maybe it's intermediate, so I might say, I'll get the thing running again, try and improve its state, and maybe it goes back to 90% of what it was. So if maybe it failed after 1,000 hours, I can improve it back to what it was like after only 100 hours. So I can do an intermediate improvement in its condition. I can add that. Now I can also create inspections. Now an inspection can actually perform 2 functions. One, it can function as a fault finding task where I'm looking for hidden failures in my system, a failure that I cannot detect straight away. So there it is, the checkbox on the failure tab for dormant failure. I can check that to tell the program that if this component fails for this problem, I may not be able to detect it straight away. And then I might have an inspection to check for that problem. Now, alternatively, I can use it for condition monitoring, and I can have an inspection that checks to see if a failure is imminent, and if it is, maybe trigger some kind of maintenance to prevent that problem from causing a failure. So I can create an inspection, again, say how often it takes place, and most of this is identical to a scheduled task like a PM. But you'll notice there are no spare parts because I'm not changing the system in any way, I'm just looking at it. And the other difference is there is a predictive data tab where I can tell the program how likely it is that this inspection will find a problem if it's there. So I might say, well, I can detect a problem up to 1 month in advance, maybe by checking for hotspots or for vibration. And I might say that I have a 99% chance of detecting a failure if it's about to occur. I can even say how that probability varies in the run-up to failure. So is the probability constant? Is it a step probability? Or maybe it increases linearly or exponentially as you get closer to the point of failure. I'll just keep the step option. And if I define an inspection like this, maybe it takes 30 minutes at a cost of $150 and I need an engineer to do that. If I set up an inspection like that, during the simulation, if an inspection occurs and it detects that this cause is about to fail, it will trigger any planned maintenance tasks in this cause that have the secondary action checkbox turned on. So you can see by default, our PM has that box turned on. So if the inspection finds a problem, it can trigger that PM. Now I can define as many planned maintenance tasks and as many inspections per cause as I need. I can turn them on and off and see which options work best. So maybe I can turn off the inspection and see how that works. And there are other types of strategy that you can model as well. For example, a condition alarm, where instead of inspecting regularly, you have an automated system that is monitoring your system continuously and will trigger PM if it detects a problem. You can see the predictive information is actually quite similar to an inspection. You can model the cost and the impact of commissioning. So if you have a failure that follows a bathtub curve, so there is infant mortality, you might do a few months of commissioning so you can remove those early life problems from the system before you begin normal operation. And you can include the costs of doing that. And you can also include the cost of any redesign. So if you've built a model that's based on your original system, but with some proposed improvements, you can include the cost of those improvements in your model as well. Now I'll come back to this dialog shortly, but for the moment, I'm going to click OK, and that will create the cause. And as I've said, you can have as many causes per functional failure as you need. So we've looked at the functions, functional failures, and failure causes. What we also need to think about are what are the effects of the failure causes as well. That's a very important part of RCM. In RCM cost, you can define effects here. So I can add an effect. So maybe I have an effect that represents production loss. And I can say how much that will cost me. And also I can input severity. The severity represents the impact of a particular effect on safety, operation, and environment. These values are dimensionless, but you might have a unit in mind that you would use. For example, if you were using the safety severity fields, you might enter safety severity in terms of a number of fatalities, or environmental severity in terms of a volume of hazardous material that's been leaked into the environment. You can use any and all of these boxes for a single effect. For me, I'm just going to say a loss of production would result in, say, 10,000 per hour loss while that failure continues. Again, I can mix and match these things together. I'm not limited just to using one field. I might say this also has an operational cost where maybe I'm losing up perhaps 10 units of product per hour. So I can click OK, and that creates an effect. I can have lots of effects in a project. That's very common. I can go into the equipment, go into the cause, go to the effects tab, and add an effect. I can select the effect that applies to this cause, and then I can say what types of outage it applies to. So I might say it only applies to failures, or maybe it applies to failures and planned maintenance. So you can check the boxes depending on which of the outages this applies to. So it could be all of them, or just two of them, or one of them. And you can also put in place a redundancy factor. The redundancy factor is essentially the probability of failure on demand of any backup you have in place to prevent this effect. A common example would be a fire. If you have an effect that represents a fire occurring, the redundancy factor might represent the probability of failure on demand of any fire protection system that you've put in place. I'll leave that at 1, so that means that if the failure occurs, we will definitely lose production. But I might add another effect. I can actually create an effect through here as well. I'll add an effect. I might call that one fire. And I'll say it has a safety per occurrence of 10. So as soon as there's a fire, we might result in 10 casualties. And then I might say the redundancy factor is 10 to the minus 4, let's say. Maybe that's the redundancy factor for my fire protection system. So I can have multiple effects per cause. So we've now built up a fairly simple project. What we could do now is maybe look at one of the main things that RCM cost can do, and that is to help you select and optimize a maintenance strategy. So there are a few ways of approaching this through the interface. For our example and our understanding, perhaps the best way to do it is through the cause itself. So I'm going to pull up the cause. I will go to the strategy tab, and on the strategy tab, the program will list all the maintenance strategies that we currently have in place. So right now I'm just doing planned maintenance once per year. Now at the bottom here, I can run a simulation of this cause. The simulation will be run over a certain number of lifetimes. I can set those in the project options. So I might say the life of this system is 20 years. I'll set that in hours. And maybe I'll do 1,000 simulations. The more simulations I can do, the more accurate my results will be. But I have to balance that against the amount of time that's needed to actually do that analysis. I'll go into my strategy tab again, run an analysis of this cause over 20 years, and there I get some results, an estimate of cost, an estimate of safety criticality. But perhaps the most important thing I'd like to look at here is the cost-benefit ratio. This is the ratio of the cost of this cause if I do the maintenance as I have it here against the expected cost of simply running to failure. And you can see that value is significantly less than 1, which suggests that my maintenance is actually worthwhile. I would be saving about 75% of the cost of running to failure by doing this maintenance. But it's possible we could actually improve on that. So we can go to interval optimization, highlight that task, click interval optimization. Here we get the optimization dialog. Optimization works by simulating the cause with a range of possible maintenance intervals and recommending the interval that gives the lowest cost. So I'll go to this button, and this will allow me to set the intervals that I want to try. So I'm going to try 50 possible maintenance intervals at increments of maybe 1 month. So that means I'm going to try doing the maintenance once a month, then once every 2 months, every 3 months. Hopefully what I will see is a minimum that indicates when I should be doing this maintenance. So I click OK, and I can run the optimization, see the progress at the bottom, and I can see there's actually a very clear minimum at about 3,650 hours. So maybe that's sort of about the 4 or 5 month mark, maybe 5 months. So that's in the cost plot. You'll notice also that the program is plotting criticality as well. So I can see how the criticality changes over time. Now, I can set criticality targets in the project options. Criticality targets indicate the maximum severity per unit time that I'm willing to tolerate. So that might be the maximum number of fatalities per hour that I am obliged to reach, or the maximum amount of material leaked into the environment. So I can put that on the plot, and for the recommended interval, the program will compare the corresponding criticalities to those targets, and if they exceed the targets, the program will warn me that it can't recommend the optimum interval because I wouldn't be meeting my criticality target. In this case, I've not set any targets, so we should be okay. I can accept the recommended interval, and that's updated in the dialog. If I run again, you see the cost-benefit ratio has actually dropped. So now, from saving about 75%, we're saving something more like 81 or 82% of the cost of running to failure. So this might be how we would go about optimizing an existing maintenance task, but maybe we could try some alternatives, do a kind of what-if analysis. What if, instead of doing planned maintenance, I only inspected the equipment and performed planned maintenance when the inspection indicates that there is a problem? So I might turn off the planned maintenance, turn on the inspection, maybe do an optimization of this, maybe do 50 intervals at increments of maybe 1 week, and run those. So it'll be a little bit slower because we've got much more going on. You can see there's a very clear optimum there at about 672. So maybe we can zoom in on that a little bit, make it so it's 50 days that we're trying. So do the inspection once a day, every 2 days, every 3 days, and so on. So again, you can see it's a little bit slower because the program's having to simulate many more tasks because the interval is so short. But you'll see it gets faster and faster as the interval gets longer. So there's my increment, there's my optimum, and it's actually, when I zoom in, a bit closer, a bit higher up, so about 720 hours. So I can accept that recommendation and run the analysis. And you see here the cost-benefit ratio is pretty good, but maybe still not quite as good as if I do the planned maintenance. So I can use this to help me to make my maintenance decisions. Do I expect planned maintenance to be better? Do I expect inspections to be better? What if I got rid of both of those and just had an alarm instead? So there are lots, so I can try lots of different options and see what works the best. Now, maintenance optimization isn't the only kind of optimization you can do in RCM cost. You can also optimize the number of spares that you keep in storage. If you remember, when we defined our spare part, we said we're keeping 1 spare at level 1 and 5 at level 2. But is that enough, or is it too much? Are we getting too much downtime because we're not storing enough spares, or are we paying too much money for spare parts storage because we're never using all these spares that we're storing. So what we can do is switch to the plot view. Maybe we'll select the maintenance optimization, the spare optimization plot, highlight that spare, and I can ask the program to try a range of potential spare parts storage levels. So I'm going to try maybe 1 to 5 at level 1, and 0 to 5 at level 1, 0 to 10 at level 2. So the program is going to look at every possible combination of numbers of spares on-site and off-site and let me know which is the most cost-effective. So I can run that, and the program is suggesting that I should store 1 spare at level 1 and 1 spare at level 2. And it's doing that by getting the balance between storage cost and unavailability cost. So you can see very clearly that if I don't store any spares, if I have 0, 1, and 2, I have a very high unavailability cost because every time there is a failure, I have to wait for 1 month while a new spare arrives. However, if I store a lot of spares, you can see that blue bit of the chart bar is a bit higher, meaning that I'm paying lots of money to store spare parts, many of which I'm not going to use. So the best optimization, the optimum level appears to be to have 1 at level 1, 1 at level 2. I can accept that recommendation. That will update the spare. I might expect to see an overall improvement in the cost of my system. So we've looked there at a fairly simple example. What I'd like to do is maybe take a look at a slightly more complex one before we take a look at some of the other features. So I'm going to see if I've got one nearby. So maybe that's not the one to look at. Right, so if you bear with me for a moment, I'm just going to find an appropriate example. Shouldn't take too long. Okay, so maybe this one. So this is a slightly more complex example. It's a kind of generic oil and gas example. We're looking at a choke valve in a wellhead. And here you can see we've got a function for that choke valve, various functional failures, and then the failure causes associated with each of those functional failures. We've got effects, spares, labor. You can see on the right here a nice maintenance optimization plot. One of the things I wanted to show you here was another feature which we didn't see in our previous example, and that was the task group. In the real world, often what you'll find is you're not just dealing with one task at a time, you're actually dealing with groups of tasks that maybe share a labor category or are performed at the same interval, maybe because it's more convenient to do it that way. You can model that in RCM cost by creating a task group. You can see that here. You can create a task group using the button on the toolbar, and you can say, what is the common maintenance interval associated with that group? What's the total operational cost of that group of tasks? You can even specify an efficiency factor that indicates how much you can improve the duration of the task by having it as part of this group. So maybe if I have a 10-hour task, it's reduced to 7.5 hours as a result of being part of this group because it's more efficient. I can then go and find tasks. Let me see if I can find one. So there's a planned maintenance task for the contamination failure, and I've made that a member of task group MP001. And then I can actually optimize that whole group of tasks as a single entity. So if you're accustomed to working in an ERP system, this might be quite familiar to you. If you know SAP, then a task group is like a maintenance plan header with the tasks inside it like the operations in the task list. If you're used to Maximo, then you might think of a task group being more like a job plan. and maybe the tasks are like route stops or something like that. So you can optimize that whole group as one entity and then apply that optimized interval to all the tasks in the group. Now, the other thing I mentioned that we haven't really looked at closely is the viable analysis tool. The viable analysis tool is provided with the RCM cost module. It's just included with it. And what it allows you to do is analyze historical failure data and use that data as part of your simulation. So let's take a look at an example. I'm going to switch to the viable module. There, I've already got a viable data set created. So I can create lots of viable data sets, but I've got one here already. Within that viable data set, I've got my historical failure data. I can see that in the grid at the bottom. So there are two different formats in which you can import that data, and you can choose the format you want to use on the analysis options for the data set. Method 1 is the method I'm using here. It's the user specified life, where I have maybe had 50 choke valves, and every time one failed, I made a note of how long it lasted for before failure, and I import those times into my data set. Alternatively, you could use method 2. Under method 2, you would import the installation date and the failure date, and then the program would infer the time to failure from those dates. Now, you can also pull this information from SAP and Maximo, and of course, they will have these install and failure dates as well. So that's the format you would get the data in if you were pulling the data from SAP or Maximo. When you import that data, the program will automatically plot the data points on a cumulative probability plot like this one, with a time across the bottom and an estimate of unreliability on the y-axis. And then all you have to do is fit that data with the relevant failure distribution. In this case, I've gone with a 2-parameter viable, so I'm going to get back a basic set of viable data for this information. So based on the historical failure data, based on the real failures that I've observed, the program estimates that the life of one of these choke valves is about 500,000 hours, and that they exhibit a kind of fatigue, so that roughly linear wear out over their lifetime. Now, you can ask the program to recommend a distribution, but we suggest that you only do that if you have a lot of failure data, because if you don't have much data, then the program will probably just choose something that has a lot of degrees of freedom and will best fit the few numbers that you have. So it's much more reliable if you have a lot of data. Otherwise, it's better to kind of use your own judgment as to what you expect to see. So we ask the program to fit the data, and it gives us those numbers, and then we can use that in RCM cost for our simulation. We go back to RCM cost. I'll make that a bit bigger. And I think under the breakage cause, if I open that and look at the failure tab, you can see I've selected the viable set choke, and it's pulled in the results of the viable analysis. And the program will then use that when it's simulating the failure. So when I'm optimizing my maintenance, now my recommendations will be based on the behavior that I'm seeing in the real world. So maybe the last thing to take a look at in RCM cost itself is actually analyzing the whole project, because I've shown you how to analyze individual causes through the strategy tab, but you can analyze the whole project and then get aggregated values of cost, criticality, and so on. To do that, just run the analysis from this green light button on the toolbar, and then the program will give you a summary of the results from the simulation. So I can get detailed breakdown of the costs based on the types of maintenance I'm doing, the resources I'm using, and so on. I can see availability data from individual failure causes throughout my system. I can see the effects, how often the effects occur, how much they're costing me, what the criticality is. And I can see how many spares I expect to use over the lifetime and how much that will cost. And of course, you can also see information about labor and equipment, how often you're calling them out, how much that's costing, what types of maintenance they're being used for. And results information is also available in the form of plots. As you've seen, we've had a look at the PM plot, optimization plot, and we've had a look at the spare optimization plot, but there are lots of other plots as well. Things like, say, a cost profile that shows you how your costs break down over the lifetime, or maybe even more useful, the contribution plot, which shows you how much each failure contributes to things like cost or availability, and how that contribution breaks down. So that is an overview of the RCM cost module, with a little bit on the side about how it works with ERP systems, with import and export, and with the variable module.